All right, so we're doing the collision lab, and this is the last part of the analysis. We're testing to see whether conservation of momentum holds. Okay, so on the left-hand side here, I have my data. Remember, in this experiment, what we were doing is we were taking a cart. Let me just sketch it right here. We had two carts. There was a heavy cart right here, and there was a light cart. I'll kind of draw them like this. And the heavy cart initially had some velocity. So that's the velocity of the heavy cart initially. And what's going to happen is it's going to be rolling along the track, and the light cart is initially sitting still. They're going to, so this is the initial situation, and then they're going to hit each other, and then they're going to stick together because there is Velcro between them. So here was the heavy cart and the light cart now stuck together. They're acting like a single mass, and then they were traveling at a final velocity. So the velocity final right here. Okay, so what we can see here is from about 0 to 1 seconds, nothing was happening. I pushed the heavy cart, so this slope represents the initial speed of the heavy cart. The collision is happening right around between 2.4 and 2.8 seconds. And then of course, we have this motion detector set up over here that's sending out these ultrasound signals. There's a cone right here that is reflecting these signals back. And so it's really measuring the speed of the heavy cart to start with. When they hit each other, then it's measuring the speed of both carts going together. So let's go ahead and do a fit here. So let's take this region of data here and do a linear fit. Okay, so this right here. So the initial speed, so the velocity of the heavy cart initially was, according to this slope, 0.3442 meters per second, 0.3442 meters per second. And that, by the way, once we know the mass of the heavy cart, that is going to give you the momentum of the heavy cart initially by taking the mass of the heavy cart times the initial velocity of the heavy cart. And up here, I have the heavy cart mass is about 1.07 kilograms. So you can figure that out. Okay, and then after the collision, let's take this section of data right in here. This is after the collision. Let's do a linear fit right there. Okay, and you can see the slope changes. So the velocity of both the heavy cart and the light cart, I'll just write that as the velocity final, is, what do we have here? 0.2429 meters per second, 0.2429 meters per second. And once again, that will give you the momentum of this entire composite system final would be the mass of the, I guess, the heavy plus the mass of the light, because that's the mass of the whole thing, times the velocity final. And we know the mass of the light cart is just under 500 grams, so about a half a kilogram. Now the idea is you want to determine if conservation of momentum holds. Now remember, let me just give you a reminder, conservation of momentum follows from, it's not an independent principle, it follows from Newton's third and second laws of motion. So let me just remind you this. It says during a collision, the force acting on the heavy cart is going to be equal in magnitude, and I'll put a minus sign here because opposite in direction to the force acting on the light cart. So this is Newton's third law. And then Newton's second law says this force acting on the heavy cart is equal to the, I'll just write it as a change in momentum of the heavy cart during the time interval of the collision is going to be equal to, negative sign, this force on the light cart is the change in momentum of the light cart during the time of the collision. Now, since the time of the collision, delta t is the same on both sides because of course the forces are acting only when they're in contact with each other, which is happening during the same time interval. So I have the change in momentum of the heavy cart should be equal to the negative of the change in momentum of the light cart. This negative sign here indicates that these forces are in opposite direction, so I'm being a little bit careful about this. What do we mean by the change in momentum of the heavy cart? I mean the momentum of the heavy cart final, that is after the collision, minus the momentum of the heavy cart initial, that means before the collision, that's the change in momentum of the heavy cart. And then put a minus sign over here. From that minus sign, this would be the change in momentum of the light cart final, that is after the collision, minus the change in momentum, the momentum of the light cart initial, that is before the collision. Okay, now here's what I'm going to do, is I'm going to move the final both to the left-hand side. So I have a momentum of the heavy cart final. And I'm going to move this over to the other side, so I'll get a plus sign plus the momentum of the light cart final equals, I'm going to move this one over to the same side as this one, so I'll get the momentum of the heavy cart initial, that's before the collision, because the minus sign here will become positive on the other side, and you've got two minus signs here, so this becomes positive, plus the momentum of the light cart initial. Now, why am I going through all this? Notice that this is the final situation. This is the final momentum of our entire system. The heavy cart final plus the light cart final, that's the final momentum of our system. And it says that should be equal to the initial momentum of our entire system. That is the momentum before our collision, which was just the momentum of the heavy cart before the collision plus the momentum of the light cart before the collision. That's the initial momentum of our whole system. It should be equal to the momentum of the heavy cart after the collision plus the momentum of the light cart after the collision. That's the final momentum of the system. In other words, the final momentum of our system should be equal to the initial momentum of the system. And so what we're really doing in this part of the lab is testing whether this is true using velocities and masses to ascertain whether that's correct or not. Okay, so I'm going to stop there and let you do the analysis.